and welcome to Module 4 from the first sprint of Lambda School Data Science. And though you're not done yet, congratulations for getting to the last module towards the end of our first sprint here. I hope you're feeling pretty good. I know we've been covering a lot of sort of big conceptual things and hopefully having some fun thinking about the scope of data science. We will, as the sprints continue, start getting into many more specifics and more depth and all of that good stuff. But to close out this week of considering dealing with data, we're going to talk about making data-backed assertions and what that means. Really, why do we look at data? Often it's because we want to draw some conclusion about a situation, right? We want to make an argument, and we want to have that be principled. We want to support that conclusion with evidence. In a business situation, maybe we are advising the decision makers, the managers, on a policy or a strategic choice, a design decision about a product. In an engineering situation, maybe we're investigating a process and trying to show the optimal approach. A lot of data is actually not about directly doing something to a consumer product in tech, but it's about optimizing operations, internal things, and that might be more of an engineering problem. Figure out how to minimize load across a bunch of servers. If you're running thousands of servers, that can be an important decision. So the common denominator, though, is regardless of the domain, if the goal is to get generalizable truth, and let's take a second and think, what do I mean? What is generalizable truth? It means that we're looking at the data we have, but we want to say something that's true in general, that would be true for more data from the similar sort of process, that is somehow representative of some sort of broader situation. You could think about it as somehow Platonic if you wish to go back to Greek philosophy. And if you don't, that's fine. But the point is science, right? That's our tool. But the real world is messy, right? It's not a lab. And business and academia even, there's mixed incentives. That is to say, sure, we want the truth, but we also want to make money, or we want to get tenure, or perhaps we just have our own biases. Who generates and tests hypotheses in perfect isolation anyway, right? Like it's this nice ideal to talk about the scientific method and first you make your hypothesis and then you go to the lab and then you poke the mouse and etc., right? You test it. That's nice, and in limited situations it really does work like that, but usually not. So what are our principles? As data scientists, there's that word science, we do attach ourselves to this belief and to this way of approaching things. What should our dictum be, though, since we're not sitting in a laboratory? Well, before I go to the next slide, I want you to think about this because I want to acknowledge there's not universal consensus or agreement on this, and there isn't a single objective answer, correct answer. I will offer you my strong opinion and highly suggest you strongly consider it, but ultimately you need to derive your own principles and approach in this field, and that will be part of your professional career. So with that caveat out of the way, fit the model to the data, not the data to the model. Okay, fit the model to the data, not the data to the model. And it's worth repeating this a little bit, partially because you don't want to get it backwards, but partially because it's saying something that is really important. And we haven't gotten to the actual techniques of predictive modeling yet, say, but you have an intuition for what that is. Everybody does. A model, a mental model, is just an explanation. It's just saying, hey, this is how we are explaining this process. This describes the causality or the correlation or what we think is going on. This explains it. And our goal as data scientists is to come up with, that's what fit means, come up with a good, optimal model, explanation, for the data that we get. We do not want to fit the data to a model. We do not want to come into a situation and say, oh, we've already got our mental model. We already know what's going on. What's going on is this is the decision, right? This is what we should do. And, oh, okay, well, now we've got data. I guess we need to make the data align with that preconception, right? And you might even laugh and think, well, who really does that, right? That seems pretty obvious. Why am I emphasizing this? Well, I can say that, again, both industry and academia do this, and it's more subtle than you might think, and it's not because people are nasty or unscientific, at least intentionally. It's because it's hard to really do this. So I'm going to say it one more time here. Our core principle as data scientists is to fit the model to the data, not the data to the model. All right. What are some specifics? Well, again, some of this will continue to make sense as we learn more depth about modeling the statistical technique. But again, model in this context really just means mental model, not necessarily regression or neural net or something. It certainly can be those things. In any case, we need test and train splits of data. You saw a little bit of that in the intro course. You need to split it, you need to use it. That's important. Otherwise, you end up with overfitting, right? And that's one form of violating this dictum. Also, try a variety of approaches. Now, start simple, right? And don't feel like you have to try everything. There's so many models out there. But don't just get really used to saying, oh, I'm going to just do this one approach to every problem I see. Well, no, we have a lot of tools in our toolkit. We're supposed to use them because this is a varied area. So those are some do's. How about some don'ts? Well, don't let your pre-analysis beliefs make you blind to the actual results. That is to say, be willing to update your beliefs. Go into a situation, be willing to change your mind. That's hard. And that can be really hard, actually. I don't think there's any great trick to it. Just constantly reminding yourself of it consciously, at least, is one good thing. Another way I like jokingly talking about it is be Bayesian. We can talk about Bayesian statistics if you want, but it's a way of thinking about statistics that involves having beliefs and updating those beliefs in light of new evidence. So be Bayesian. And another important don't is don't massage your data. Maybe you've even heard that term, data massage. I tend to say that that's not a good way to think about it. You should clean your data. That is necessary. If there are missing values, you have to do things so your algorithms even run. But the manipulations of your data, when you clean it, or really when you do anything, they should not be correlated with the actual analysis, with the signal in the data, or at least with the problem that you're trying to solve with the data. And so massaging, well, if you're kind of squishing the data here and there to try to, oh, let's de-emphasize this part, emphasize that other part because it'll be a little bit more flattering. Right? This is a lot of, as you become a data scientist, you'll become a bit more sensitive when you read news and see oh, top X lists of something, and you'll realize, yeah, sure, they're basing this on data, but they're kind of just making up an arbitrary linear combination of things and deciding okay, that means that whatever Wisconsin is the best city to live in based on this, right? And it's not data science. I won't speak more for what it is, but it's not data science. So don't do that. But as I said, it's not always so obvious. So think of an example. Suppose you're a researcher and you're assessing the effectiveness of some drug X, right? That sounds like a nice example drug. And you can't run a controlled trial because whatever the limitations, you're studying the effectiveness of it, but you're not actually in a situation to do a proper double-blind study. But you do have data on who purchased the drug, right? And you have data about whether or not they recovered, right? Whether while they were taking the drug, they got better from whatever the condition the drug is supposed to help treat. And you even have data on people with the condition, but didn't take the drug, right? Okay, so you've got data on people who took the drug, data on people who didn't take the drug, and they all have the condition, and you can see whether they're getting better or not. That's great, right? That feels like, okay, that ought to be enough. We ought to be able to tease out something kind of like causality. What does drug X do to this condition? Oh, right? You count all the people who got better while taking the drug. You divide by the total of drug-taking people, both, the people who got better and the people who didn't. Count all the people who got better without taking the drug. Divide by all the non-drug people. And if the first result, if more people got better while taking the drug, relative to people getting better without taking the drug, huzzah, drug X does something. Pause and think. Are there any problems with this? All right, I hope you paused. Well, yes, right. There's all sorts of potential problems, but one particular one that we can think of is called confounding variables. This can also be called omitted variable bias in some situations, often when you're actually fitting a more predictive model. But regardless, what we mean is there's just some other part of information, some other feature of your observations, if we want to try to be a little more precise in our language, that has to do with multiple of the other things that we care about that we're not taking track of, right? We kind of already talked about this way back at the beginning of the week with pirates and global warming, if you recall. But that was a silly example. This is a fairly realistic one. And in this case, well, let's say the drug, for whatever reason, is marketed in a way such that the people who even take it's related to their gender. It's marketed, say, such that males are far more likely to buy and use this drug. But the condition is still a condition females can have, say. And let's also say that the actual recovery, the likelihood of getting better or how one gets better, is also related to gender, right? That's fairly plausible. Gender can matter for various health conditions. So we've got this other variable out there, gender, which both impacts whether or not somebody takes the drug, and it impacts whether or not somebody gets better. And because of the existence of this other variable, it's not as simple as just saying, okay, well, more people who take the drugs get better, that means the drug's doing its job. Well, no, we don't know. We need to actually also figure out the gender of all these people and add that to our analysis. And that's exactly what we'll be stepping through in the later video and also together live. Now, there are much more sophisticated techniques to handling it. We'll just sort of look at these simple examples in more depth. But the point is if there's a confounding variable, you need to consider it. And so, as I said, it isn't like, oh, malice on the part of scientists for not thinking about these things. It's that these things are hard. So, keep revisiting these issues. You're just starting out, nearing the end of your first week here, and it may seem obvious that, oh, data science should just do things right, yeah? Be honest and consider all the data. But it really does get more complicated. Even that previous example was kind of idealized a bit. And another thing that I want to note, and this again is subjective and psychological, but working on a problem for a long time tends to cause people to become attached to it and to particular aspects of it, to whatever, initial beliefs they formed. And, there's sayings that, and there's stories that science progresses, one funeral at a time, and similar sort of dark sayings, which is to say that, Einstein's theories, his contemporary physicist buddies did not like them. It was really only relativity was really only broadly accepted when a whole generation of physicists changed, rotating the guard, right? And obviously, we would rather be able to update our beliefs short of shuffling on, and there is no magic way to always do this. But test and reflect, and that will help. And there's some good news here too. There's lots of advanced techniques that help with this, that help testing and evaluating the goodness of fit or the validity of an analysis. And that is absolutely one of the most important toolkits or things to have in your toolkit as a data scientist. So we will be covering those in much more depth. So thank you. Here's the source for that confounding variable illustration. There's a whole article on it on Wikipedia if you're interested. And please continue thinking about these things. It can be a very interesting discussion. So come to the lecture with questions. Thank you.